Today we're graphing tangents and cotangents. This starts off by asking the question, is tangent an even or an odd function? We'll come back and answer that once we have the picture drawn. It'll be easier to describe at that point. And we're using this to indicate where the critical values come from to give us the properties that we want to use. And we know that tangent is defined as this ratio, sine over cosine. And from the unit circle, we know sine is corresponding with the y-coordinate and cosine with the x-coordinate. So think of it as the y over the x-coordinate. So at 0 radians, y over x, that results in an output of 0. At pi over 4, y over x is exactly 1. So that's why we're using these angles at intervals of pi over 4 as opposed to like pi over 6, because we'll get really nice outputs. That makes it easy for us to plot. At pi over 2, we have y over x. We're dividing by 0, so that's our undefined. That's where we'll get a vertical asymptote. Here at 3/4 pi, we'll have an output of -1, and pi, we're back to 0. So we're going to see the same pattern repeating as we go through the bottom half of the circle. Here in quadrant 3 at 5/4 pi, we'll get a +1. Here at the bottom, we're dividing by the x-coordinate of 0, so that's our undefined. Here at 7/4 pi, we have a -1, and then back to 2 pi. So we're going to see our vertical asymptotes here, where you see the undefineds, and then we'll have 3 critical points to plot. So we're starting with a low point, increasing to 0, and then getting to a high point at 1. So we're going to see an increasing pattern. Let's go ahead and detail that out here. So each of these grid lines on the horizontal axis will be going in terms of 1/4 of a pi. So just like what we saw on the table, that's what we'll be having here. So pi over 4, then pi over 2, and so on. And then a couple here on the left-hand side, -pi over 4 and -pi over 2 as well. For my vertical scale, there's 1, 2, and so on. All right, so here we have at 0, we have an output of 0. Pi over 4, we have an output of 1. Pi over 2, this is our vertical asymptote. At 3/4 pi, which is here, that's a -1. Then at pi, we have 0. 5/4 pi, we have +1. So there's the 3 critical points in that ascending pattern. 3/2 pi. Here's our next vertical asymptote. 7/2 pi, that's at -1, and then 2 pi is at 0. So here in the middle, we see a complete cycle. So this is our tangent. It's an ascending pattern from left to right. And what that means is we have another branch that's broken up. There's the top half of a branch. Here's the bottom half of a branch. That's our pattern. The issue is that we want to graph a complete branch. We don't want a broken branch. We don't want half of a branch. And we're not using this one here when we can use one that's closer to the origin, right? So we always want to try and do this. So we're going to copy and paste. Take this tail of a branch, copy it, and paste it right here. So that way we have this critical point at 2 pi, which matches this critical point at 0 pi. And then this critical point would be located right here at -pi over 4. And then this vertical asymptote would be pasted right here at -pi over 2. So that's what we're looking at doing. So you have 2 complete cycles in a rotation around the circle. What we'll be doing today is we will be looking at just 1 cycle, because this is just repeating the first cycle. Instead of graphing 2, we'll graph 1. Again, a lot of math classes will say to graph 2. Here I'm just emphasizing 1 cycle. And 1 cycle is a period of length pi. Okay? So what that means is we are starting our pattern here, not at 0, but at -pi over 2. We're stopping our pattern here at +pi over 2. So this is different than sines and cosines. With sine and cosine, we started at 0. Now we're not starting at 0. With sines and cosines, we stopped at 2 pi. We're ending at pi over 2. All right, so those are some key differences. So we want to come back and answer this question, is this odd or even? We've looked at this before. It has to do with symmetry. So if we were to take a look at our graph around the origin there, we want to know, does it have some kind of reflection? Can we reflect it over the y-axis? No, it does not map onto itself. That would describe even symmetry. Instead, what we have here is rotational symmetry. We can rotate it 180 degrees and it maps onto itself. So that's what we're observing. It is an odd function, and what that means is it has rotation symmetry of 180 degrees. A rotation of 180 degrees maps it back onto itself. Right. And we see that here because of the outputs, right? We have a positive one and a negative one. That's what gives it that symmetry. All right, so we have a period of pi. We'll do the domain in a minute. Let's talk about the equation of the vertical asymptotes. We have two terms. The first term describes the span from one to the next, so that's the length of our cycle. So pi times n. N is just the counting of our first, our second, our third, and fourth, and so on, vertical asymptotes. And then if the first one doesn't start at 0, where does it start? It starts here at negative pi over 2, so minus pi over 2. So it's like a little equation, if you will, where you could calculate the location of any vertical asymptote. You just drop it in for n. You could find the 100th if you wanted to. So that is describing where no points are plotted. So that will then help us inform our decision about how to communicate. What is the domain? The domain describes where we do have points plotted. The vertical asymptote is where we don't have points plotted. So the domain is all real numbers except not here. So we'll say x does not equal, and then we'll just copy that little equation down all over again. It's a way of saying I have points everywhere, but not here, not where I would find those vertical asymptotes. The range is the output. We have y-coordinates from negative to positive infinity. So those are some of the features. For us, what's important is remembering the period length and then what we're doing for our start and ending patterns. Okay, that's what we need for graphing. Notice that where you are starting is a vertical asymptote, and where you are ending is also a vertical asymptote. So that's repeated down here in the middle. When we're going to be graphing a tangent function, oftentimes we'll have a value of b, maybe a value of c. Usually these are wrapped in parentheses like that. So we say we take everything in the parentheses, take both b and c, take what you see here, and set it equal to negative pi over 2, which gives you the starting location, which also gives you the vertical asymptote. And then take everything in parentheses and set that equal to positive pi over 2 for the ending location, which is also a vertical asymptote location. All right, so let's take a look at example number 1. We're going to graph negative 2 times tangent of 2x. So this is the A, this is the B. Notice with the negative sign, we will have a reflection. So we'll see what happens here in a moment. No horizontal or vertical shift. So the amplitude, absolute value of A, that'll be a positive 2. The period, now remember, the period is pi, but it's going to be modified by the value of B. So it's pi over b. That's what we want to do to calculate this. So for us, pi over 2 is the length of that period. We'll take that result and divide that into fourths. And so when dividing fractions, multiply by the reciprocal. In other words, our scale will be pi over 8. So that'll set the horizontal axis, counting in terms of 1/8 of a pi. So there's 1/8 pi, 2/8 pi, it's pi over 4, 3/8 pi, and then on the left-hand side, and so on. If we need more, we'll add more. Now we do want to know where are we starting and ending this pattern, and I don't have that printed here as a provided attribute to find, so we'll just add it in right here, start and end. Okay. We're going to take everything in the parentheses, which is always describing the b and the c. Right, we don't have a value of c, so we're taking the 2x, And we set that equal to where our tangent graph normally starts, negative pi over 2. Work to isolate the variable, so divide away that 2, and you have a negative pi over 4. So that's where we're starting. That's also the location then of a vertical asymptote. Where are we ending? Take everything in the parentheses, which is 2x again. Set that equal to positive pi over 2. That's where the parent function of our tangent graph normally stops. So we are ending at pi over 4. And that's also where the vertical asymptote is located. Now, when you do this, double check. You should find 3 tick marks evenly spaced that are in the middle. That's where the 3 critical points go. So you have one here at negative pi over 8. You have one here at 0. And you have a third here at positive pi over 8. So yeah, 1, 2, 3. So we do that. If you have, more or less than 3, that means your spacing is off. Our midline is the value of d, which in this case is just 0. And we really have no max or min. This is kind of left over from when we were graphing sines and cosines. There's no max or min because the tangent graph will go up and down forever. The equation of the vertical asymptotes, all right, so it'll be x equals the distance from one to the next. If you're not sure, use your scale to count those tick marks. We're counting in terms of eighth of a pi. So starting here, 1/8 pi, 2/8 pi, 3/8 pi, 4/8 pi. That's the span. So 4/8 pi simplifies to pi over 2 times n. The first one is starting here at negative pi over 4. All right, so we're now going to finish up our graph. We'll use a scale here, just counting on the vertical scale by ones. The midline at 0 is still on the horizontal axis, and the amplitude being 2 tells us where we will have a critical value, and also at negative 2 we'll have another critical value. So remember, tangent is an increasing pattern, and then we'll reflect it here in just a moment. So our tangent graph normally goes in the pattern of lowest to middle to highest point. So we would go on this first tick mark. Here's our amplitude value of, there's my lowest point. We jump to the middle tick mark. There's the midline. Jump to the third tick mark, and there's the amplitude value of positive 2. So I'll dash this in because this is not the final answer, but this is what our tangent graph would look like if we were to draw it like this. So I'll label that as tangent. And then we want to flip this upside down. That reflection means my highest critical value is now going to be the lowest. And then my lowest is now the highest. So we are, in fact, positioned this way. And I'll label this as my reflected tangent. Notice in this case we did not have a vertical shift, so let me just illustrate what would that look like if we had a vertical shift. Here are our 3 critical points that came from reflecting the tangent graph upside down. There's the vertical asymptotes. Let's imagine for a moment we have had a vertical shift of up 2. So 1, 2, right? Notice it looks like those vertical lines just kind of, well, they go on forever, so they don't really appear to have moved any. But you can see that those 3 critical points, they've all kept the same spacing. They just moved up together like that. If we had a vertical shift of down 2, well, then it would look like this. All right, so let's now go on and talk about cotangents. We're going to use the same unit circle to create our points to plot. I don't think I redrew it. No, I didn't. So we're using the same critical values. You can see I set up that table there. This time, our cotangent is defined as the ratio of cosine over sine. So on the unit circle, cosine is paired up with the x-coordinate, sine is associated with the y-coordinates. We're taking the x-coordinate dividing by the y-coordinate. So anytime your y-coordinate is 0, we'll have an undefined result, and that happens right here at 0 radians. At pi over 4, we have an output of 1, then a 0, then a negative 1, and then an undefined, because at pi, our y-coordinate is 0. And then the pattern repeats itself, so we have a positive 1, then a 0, then a negative 1, and back to undefined at 2 pi. So notice these will be the location of the vertical asymptotes. You'll have 3 critical points in the middle, and notice we're descending here. We have a positive 1, then a 0, then a negative 1, so the line will be going down this way. So let's set up our scale here using pi over 4. In my vertical scale. All right, so undefined at 0. Pi over 4 is 1. Pi over 2 is 0. 3/4 pi, which is right here, that's at negative 1. So those are the descending points, and then pi is another vertical asymptote. And then the pattern repeats itself. Notice in this case, we have 2 whole branches. Neither of them are broken, but again, we just want to use 1 cycle, so we'll just be using this much from 0 to pi. So this is the length of my cycle. That's the period. And so here, for cotangent, we will start at 0. And for cotangent, we will stop or end the pattern at pi. All right, so these are some of the key differences between this and tangent and also our sines and cosine pattern. All right, so our vertical asymptote will be located at pi times n, and we're starting at 0, so you don't have to show a plus 0, but this is just so you know we took that into consideration. And that will then influence what our domain is. Our domain is all real numbers, but not here, so not where you would find x equal to pi times n. And then the range is also all real numbers. Right, so like what we saw before, you're going to take everything that's in parentheses, and what I mean by that is the b and the c, and you'll set that equal to 0, which is our first vertical asymptote, which is the starting point. And you'll set that equal to pi, which is where we stop the pattern, and that's our second vertical asymptote. So here's our second graph. 1/2 times cotangent of x over 2. So the a is 1/2. Notice the b is also 1/2. No c and no d in this case. So amplitude is 1/2. The period is not 2 pi, but 1 pi divided by b. So we're dividing by 1/2. That simplifies to 2 pi. So it's a horizontal stretch. Take that result, divide that into 4 equal parts, and this will be our scale, pi over 2. There's my horizontal axis. The midline is still 0. No minimum or maximum. Again, that's sort of left over from graphing sines and cosines. But we do need to figure out where are we starting and ending the pattern. I need that on there as well. So we take everything that would be here in the parentheses, that would include b and possibly c. So x over 2, and we set that equal to 0 because that's where cotangent normally starts. So we will still start at 0. Repeat that, this time set it equal to pi. That's where cotangent normally stops. So we will stop at 2 pi. So again, if you're starting at 0 and stopping at 2 pi, that should agree with the period that you already found. So there's my 0. So 0 then is where we find our first vertical asymptote. 2 pi as well. And then double check, you should have 3 tick marks, 1, 2, 3. Inside, that's where the 3 points will go. Cotangent is a descending pattern, so it'll look like this. So that we can fit an amplitude of 1/2 in here, I will count on my vertical scale by 1/2 like this. So there's 1/2, there's 1, there's 1.5, there's 2. Okay. So here's my midline. My amplitude takes me to positive 1/2 and negative 1/2. So we want a descending pattern here. So at the first tick mark, we're at the top amplitude value. In the middle tick mark, we're on the midline. Third tick mark, we're here. on the bottom amplitude values. So it looks like this. Right, so you want to make the ends of your tangent and cotangent curve look like they're running almost parallel by the time they get over here to the vertical asymptotes. Our equation then is 2 pi times n, and we're starting at 0, so we don't have to write a plus 0. But that'll finish it off.